Hello everyone. So today we will resume our previous lecture on the Brayton cycle. Last lecture we just talked about a basic Brayton cycle where we have a compressor, then we have a combustion chamber, the gas turbine, and then commonly we have the exit, which is represented by a heat exchanger for Q out. Um, at the end of the last lecture, we talked about there are some possible improvements we can install in the Brayton cycle, and today we are going to start with one of them, which is called regeneration. What is regeneration? Regeneration, as you can see here, is the idea that we can, instead of just wasting this heat from point 4 to point 1, we utilize some of this heat, some of the thermal energy of this exhaust gas to reheat the incoming air. What that does is it sort of A, reduces our waste to the environment, and B, it reduces our requirement for the fuel to be burnt in order to get to temperature 3. So right now you can see that instead of supplying heat from point 2 to point 3, now we only have to supply heat from point 5 or 5, yes, so point 5. So the actual heat transfer here is just from point 3 to 0.5, and similarly the actual heat rejection process is only from point 6 to point 1. So to better understand how this is happening, what is happening here, we can just look at the old equations and then the new ones. So in a regular Brayton cycle, your Qn would be H3 minus H2, and your Q out would be H4 minus H1. But in, okay, yes, it should add the regular and the regen. In the regenerative cycle, now we have Q in, you can just add a dash here, is equal to H3 minus H5, and your Q out would be H6 minus H2, because remember, from H4 to H6 you're not actually losing heat to the environment, you're just giving heat um, to the incoming air. So what that does is, in terms of efficiency of the cycle, now we have 1 minus H6 minus H2, that is the new Q out, divided by H3 minus H5. So yes, in terms of the pure efficiency of the system, you can see that you might not like get as large of an efficiency bump as you expected, because in addition to your Q incoming being low, your Q out is being low as well. So that sort of puts a little sort of bump in your efficiency terms. But even if you look at, for example, let's talk about efficiency, and let's talk about some hypothetical numbers. Let's say your Q out initially was 4 units and your Q in was 6 units. Okay, so now you can see that the amount of energy transported, given from the exhaust gas here, the amount of energy Q has to be equal to the amount of energy stored here as well, right? So let's say we were able to utilize 2 units of energy. Okay, let's solve this figure. What is this? 1 minus 2 by 3, and which will be 2 by 3 is about 66.7, so this will be 33.3%. But if we were able to reduce 2 units of energy from both sides, so now it becomes 1 minus 2 over 4, and 1 minus 2 over 4 will be 50%. So you can see that uh, regular and regeneration. So now you can see that the more we are able to save from this cycle, the more we can actually increase our efficiency and improve our efficiency. This is not exactly as linear as the example I showed you. There are cases where this regeneration is more effective or less effective depending on how we are um, solving this system, but we can commonly see that we do experience an increase in the efficiency. So in last slide we saw that adding some of the heat from this exhaust to this inlet allows us to A, reduce our fuel requirements, B, reduce the environmental waste the waste we put to the environment, and it also improves our efficiency. But if you might have noticed a little, there was a slight difference between the exit highest temperature of the um, exhaust, which is zero point 0.4, which might be equivalent to 0.5 dash, and the actual maximum temperature of the incoming air with regeneration, which is actual 0.5. So this sort of difference is represented by the regenerator effectiveness, which is called eta of regen. So the maximum possible heat generation via heat transfer which could have happened from would have been from zero point 0.4 to zero point 0.2. Like, this is the maximum temperature difference we have, but in reality we are not able to transmit most of the heat even if a counterflow heat exchanger, because let's say we have zero point 0.4 here, we are trying to get to let's say this is zero point 0.2, which is a counterflow heat exchanger, so your exhaust gas is flowing in this direction and your incoming air is going in this direction. So let's say this is 5, this is 6. So the only way you can have heat transfer here, or actually we should just say this is um, Q regen, is if this 4 and this 5 have a delta T, and this 6 and this 2 also have a delta T. As soon as there is no temperature difference between 0.4 and 0.5 or 0.6 and 0.2, there is no heat transfer possible, right? So realistically, if the regenerator or the heat exchanger between the exhaust and the intake is of finite length, you cannot have 0.4 and 0.5 to be equal to each other. So this is what is represented here. You can see the maximum theoretical regeneration could be from zero point 0.5 dash, which is equal to 4, to 0.2. So this is the maximum you could have theoretically transferred the heat from exhaust to intake, but the actual heat transfer you have is somewhere in the middle, which is 0.5. You heat the incoming air from 0.2 to 0.5 instead of 5 dash, which is the maximum. So your effectiveness of the regenerator is the actual temperature you are able to raise in the regenerator versus the maximum temperature you could have achieved in the regenerator theoretically. This effectiveness generally comes out to be around 85%, 80 to 85% in common regenerators. So Another thing we have commonly seen in Brayton cycles, because we are just dealing with air, so some of the times we can just say that we are assuming the Cp to be constant, and which results in uh, us moving from H to T. So this is the same thing that they have assumed that Cp is constant, so they have changed the effectiveness to temperature terms. This is still again relatively accurate. If you don't have the exact enthalpy terms, you can use temperature. It is sometimes effective for solving the process as well. So this is not something you should just immediately ignore, but this is not something that you this will give you the most accurate result. Obviously the most accurate result will still be from enthalpy, but with a small error you can assume Cp is constant and use this equation. Again, common regenerators are generally about 80 to 85% effective. um, so Yes, so the equation we saw in the first slide, it is written here as well. So you can see that this is H6 to H1. Now the actual heat rejection will be from 6 to 1, because 4 to 6 is uh, used in the regeneration, and similarly in Qin you need to supply heat from point 0.5 to point 0.3. Similarly, you can see that you can use this efficiency. You can change the efficiency terms in this equation as well. 1 minus T1 by T3, pressure ratio K minus 1 by K. Okay, so in the last slides we saw that there is a general increase in efficiency if we add a regenerator to the Brayton cycle, a regular Brayton cycle, and we also saw the equation actually go to 1 minus T1 by T3 multiplied by Rp K minus 1 by K. So first thing you can see is uh, the more the higher number we have of T1 by T3, the less effective the regenerator would be. Obviously, the lower we have, the lower the ratio of T1 by T3 is. That means that if we draw the TS diagram and we draw, okay, let me just try and draw a better one. So this temperature is T1 and this peak temperature is T3. The bigger the ratio of these temperatures, the more you can see that we have the more ability of the heat to be regenerated. The lesser temperature difference we have, the lesser we can use the waste heat from the exhaust to heat the incoming air. Let's just assume this system to be this regenerator to be 100% effective, because we can now move on to the next point, which looks like a little weird graph. So this is a regular and a normal Brayton cycle without any improvement, and this follows a normal curve which we expect. Like we have 30% efficiency at 5 pressure ratio, and then we have about 60 to 62% efficiency at 20 pressure ratio. But if you look at the with regeneration graph, this looks a little weird, and in the way that the more you increase the pressure ratio, the further the efficiency starts to decrease. It is apparent as you see the efficiency equation, because you can see that this Rp is now in positive terms. This is now multiplying instead of being divided. But in the sense of practical system as well. So if you have, for example, if you have the temperature ratio to be 0.2, that means that T3 um, uh, T1 is 20% of the temperature of T3. For example, if this is 1000, this will be 200. Obviously we are talking about kelvins. So let's say we talk about T3 to be 1000, T1 to be 200. What happens is uh, at lower pressure ratio, you can see that this work is so low that we have a lot of region which is available for regenerative heating. That means that this sort of actual line goes up to about 68%, which is, you can see, which is even higher than um, a cycle, a Brayton cycle without regeneration at 20 pressure ratio. So that is an interesting thing. But if you have the same temperature ratios, for example 100, 1000 and 200, and you start to increase the pressure ratio, let's say this was at 5, you talk about a pressure ratio of 10. So what happens at 10? What happens at 10 is you have this line, you have this line, and they sort of meet. Unfortunately, I haven't drawn this very effectively. Let's see if we can draw this a bit um, sharper. Okay, so now I know this line looks slanted, but just bear with me that if we have a pressure ratio of, for example, 15, so at 15 there is only a very small area which is available for regeneration. You can see that this is a very small area. You can even draw it closer. So that means that to regeneration to be effective, you need further um, temperature ratios. For example, if this was at 1500 Kelvin, then it would have been effective because now you would have had more area available for regeneration. So this implies that our system has allows for, like, the regeneration is better at lower pressure ratios, because again, as you can see here, this allows you to have a wider region for the actual regeneration to take place. Okay, hi. So now we will look at an example of the Brayton cycle. Um, as you might recall, this example looks similar to the example 9-5 I asked you to solve in the Angel book. This basically example takes use of the examples from 9-5 to 9-6 and 7. So this incorporates all three of these examples. So you can look at them individually, and now we will solve these here as well. So initially, what is given is that we have the uh, high temperature, low temperature, the inlet temperature, and the turbine inlet. So we have T3 and we have T1, and we have the pressure ratio of 8. So let's just look at the very basic example, and we get the data from the given um, the given data we use to find the enthalpy and pressure values. So you can use the table 817, I think this is for air. So the ideal air table, you can use that, and you can find out the enthalpy value here and the pressure ratios and you can use those pressure ratios to find out the new temperatures and their um, so once you have all four of these enthalpies and their sort of you can solve this a basic example of the Brayton cycle, and you get your efficiency to be around 42.6%, right? But we are also given the compressor and turbine efficiencies at 80% and 85% respectively. So now what we do is we take this this ideal compressor work and turbine work, and we calculate the actual compressor and turbine work. So in actual, compressor has to do more work than the minimum necessary, so we get more compressor work compared to the ideal compressor work, and for turbine we get less turbine work compared to ideal turbine work. Okay, so we get the uh, back work ratios, and we didn't actually calculate the exit temperatures. How we can do that is simply just add this value, this 305.20, to the H1, so we get 605. So H2A would be equal to 605 um, kilojoule per kg, and H4A would be equal to again 1395.97 minus 515, which would be around 900 something. Let me just grab my calculator. So 1395.97 minus 515.61 would be equal to 880.36. So 880.36. So you can use the table again and find out the temperature value associated with. Shouldn't add the second sign because it looks like n is equal to. So you can use this enthalpy value calculated and find out the temperatures at compressor and turbine. Okay, but next we needed to find out the back work ratio, which is calculated here. That is 59% of the turbine work is utilized back in the compressor, which is not ideal actually, but because we are dealing with the real systems, this is somewhat expected. Now you can see the efficiency of the cycle dropped from 42.6% to 26.6% because of the compressor and turbine efficiencies. Now let's add regeneration into it as well. So now regeneration, you can see, will be from 4A to 2A, and again uh, the regenerator has an effectiveness of 80%, so that means that from 4A to 2A we can only utilize 80% of the temperature difference. So now you can see our new calculations. Let me just get rid of the older lines. So starting here, unfortunately we ran out of space, so I had to add this graph on top of the older one. So if you look here, so now effectiveness means that now our H5, this unknown variable, will be equal to this point. You can see that these are the same values which we find out here as well. So our Qn is actually from 5 to 3. This is the Qn, and which is equal to 570.60. Our net work output did not change, but our Qn did. So our efficiency rose from 26.6% to 36.9%. It is still again lower than the peak efficiency of the original um, Brayton cycle, but again we have to consider the inefficiencies as well. So this means that and if you compare it to the original cycle, our efficiency increased by about 10.3%. You will use this table a lot, ideal gas properties of air. This does not require a lot of explanation on my side. Just remember the temperatures are in Kelvin and enthalpy is just the function of temperature because we are dealing with ideal gas. Okay. This table goes up to 2200 Kelvin. We will mostly restrict ourselves to the maximum temperature which is written here, but sometimes you might need to um, extrapolate the last values and just find out the, for example, at 2300 or 2500 Kelvin, you can just extrapolate this data and it's going to be okay. Another thing which is important is this PR. So in a lot of equations, when you see P2 by P1, that is also equal to PR2 by PR1. So you can use this sort of um, relative pressure ratio and find out the sort of new pressure ratio, and you can find out the enthalpy at new pressure ratio as well. So that can help you a lot as well, as seen in the previous example sort. So um, this question means that how much did we drop from point 4A to the end of regenerator. So this we can discuss in the session, but for now your task will be to actually um, derive this equation from your normal regeneration cycle equation, which is again 1 minus q out by qn, and you can use that equation and drive up to this. You can at least try and we can see the results. One other actually two other improvements which are very similar in sort of design are called reheating and intercooling. So reheating is a very simple concept. You have already seen that in steam power plants as well, that for example our fuel has some thermal energy left over it, and after the turbine we can use that energy to reheat this fuel and run it in another turbine. So in um, Brayton cycles, it looks like this. We first heat this to 0.6, for example, uh, and then when it drops to 0.7, we reheat it again to 0.8 and then use this to drive a second turbine. So this is the reheat part. Okay. Uh, So intercooling is a little similar in a way that when we start to compress gas, its temperature starts to rise. But for example, if we start just let this gas compress from point 1 to, let's say, here, what happens is we have a lot of input work, and our sort of, and we are not allowing this system to regenerate a lot of heat, and we are using this just um, a lot of temperature has risen because of the compression work, and we have not uh, utilized this system to the best efficiency. So what we do is we actually allow the gases to cool down at at a mediate temperature, at a mediate pressure, and then at point 3 which was the initial temperature of point 1, which was the equal temperature of point 1, we again compress this gas to a final temperature, and we can do that again and again. So this could look like this. So what it does is this allows a very small amount of work input to compress the gas, and then again a small amount of work input, and then again a small amount of work input to actually get the ideal um, compression ratio. But since we are rejecting heat, what is happening here is we are rejecting heat after every small compression. So when we are rejecting heat after a very small compression, what is happening? We are adding load to our combustion chamber. So if you just implement intercooling, it will actually reduce the efficiency of your system because our Qmin has to be increased. How do we implement intercooling then? We implement intercooling with also a help of regeneration. So you will almost always see a regenerator when you have intercooling in a gas turbine. You might have seen intercooler in the terms of in vehicles as well. There are some Land Cruisers, old Land Cruisers, which had the term intercooler added in them. So those actually intercoolers are used for the turbochargers. So their turbochargers compress the air and send the compressed air into the engine for added combustion. So those, again, turbochargers have multi-stages, and they install intercoolers to keep the temperature of the gas lower, so that we can have a high pressure inlet air but at a lower temperature. But in gas turbines, intercooling is almost always implemented with the help of regeneration as well. Reheating, obviously reheating is at a temperature which is much higher than the regeneration. So regeneration is not really applicable at the reheat stage, but in the intercooling it is very important to have a regenerator, because otherwise the intercooler is just adding more pressure to the combustion chamber. So ideally what you want is, for example, if our system is going from um, let's say um, 1 bar to 8 bar. So what you want to do is, you want to, or let's say 9 bar, let's say this is 9 bar. So the actual pressure ratio is 9. So where you want to install the intercooler is, you want to take the multiple of the low pressure and the multiple of the high pressure, multiple of the low and the high pressure, and you want to take the under root of it. That means that you, for example, if we say this is the P of the intercooler, that P in by 1 should be equal to 9 divided by P. So that means you want the same pressure ratio between 1 and 2 and 3 and 4. Remember that P3 is equal to P2 here. So if you add multiple intercoolers, then this obviously ratio becomes, this under root becomes, for example, a cube root. If you have 2 intercoolers, then you have, for example, this line going again. So this would be, for example, if you are going from 1 to 8 bar, then you want 1 to 2, then 2 to 4, and then 4 to 8. So that would be 8 to 4 is equal to 4 by 2, which is equal to 2 by 1. All the intercooler, all the pressure ratios will be equal. Similarly, you want the reheater to have the same pressure ratios as well. So this is what is written here. The number of intercoolers you are adding just takes the root of that numbered root of the total pressure ratio. Okay. Yes. So this is again the point. It is almost always used with intercooling is almost always used with regeneration. So without regeneration, you are just adding load to the combustion chamber, which will obviously reduce the efficiency of the system. Again, with reheating as well, you want the same thing. You want to keep the pressure ratios constant. So for example, you are going from 8 bar to 1 bar with just one reheat. So you want the um, with 9 bar to 1 bar with one reheat. So that will be 9 to 3 bar, and then reheat, and then 3 to 1 bar. And similarly, if you had two reheaters, so for example, you go from 8 to 4 and then reheat there, and then 4 to 2 and then reheat there, and then 2 to 1. Mouse unfortunately does not allow me to write that effectively, but I hope you are still getting the message. Um, so um, in the reheat and intercooling cycles, one thing important is that now we do not care at which pressure we are reheating the system from. For example, if we are talking about H6 will be equal to H8, and similarly H5 will be equal to H7, which will be equal to H9. Similarly, H1 will be equal to H3, and H2 will be equal to H4. So, and you can, so if you talk about, for example, 300 Kelvin, 300 Kelvin and overall pressure ratio of 9. So the pressure ratio of P2 should be equal to, again, because it has only one intercooler, under root of 9 multiplied by P1. So P2 by P1 is equal to 3. And then you can use the same equation you used in the original Brayton cycle example. I'm Since I'm recording this, I can't really jump between the lot of them. So you can use that equation and just find out the Wn, and you just multiply that Wn by 2, because pressure ratios are still the same. Similarly, when you go W out, you can just again take the H8 minus H9 multiplied by 2. Okay. And the Qn, let's say so it says the regenerator has an effectiveness of 100%. So that means your Q out will be equal to H10 minus H1, which is in fact equal to H4 minus H1. And similarly, Qin will be equal to, actually you need to Q that, plus we also have another Q out which is also equal to H2 minus H3. Yes, so H2 minus H3, which is again equal to H4 minus H1. So that means this is just 2 times H4 minus H1. And similarly, Qn will be equal to H6 minus H5, again multiplied by 1 and 2. So your system efficiency will be 1 minus 2 times H4 minus H1 divided by H6 minus H5, again multiplied by 2. So you can actually ignore this and you get, so you can see that the more intercoolers and reheaters we add, the smaller this number and actually this number becomes. So you can see in some of the cases it allows you to increase efficiency until a point. But again, obviously the more we have the difference between these sort of units, the more we can actually take advantage of um, the, so sort of you look like this, and the more we can have Q region. But again, as we increase the number of turbines and increase the number of compressors, the cost increases. So that is a big problem for us as well. So we can not just increase the number of turbines and compressors as we want. We have to justify the cost of every component added. So after all of this, we go to combined cycles. Combined cycles involve basically power generation from multiple cycles incorporated into one. A common example could be that you have, like for example, you burn coal or you burn natural gas. It burns at a very high temperature, and that temperature might not be that might be much higher than the temperature you need for a steam power plant. So what you can do is you can sort of burn this air fuel mixture in this combustion chamber, and then you can produce power from it, and this still a very high temperature. For example, let's say this is still at 1000 degrees Celsius, or um, maybe 700 degrees Celsius. So what you can do is you can just, instead of rejecting heat to the environment, you can supply heat to this steam power plant, which heats it up to 0.3 for example, and so you go from 0.8 to 0.9 and you supply heat from 0.2 to 0.3. So you can see that this sort of gives energy to the steam cycle. So what happens is you have utilized the energy lost from 0.8 to 0.9 in the steam power plant, which has its own inefficiency. Obviously, for example, it converts 30% of that provided efficiency, provided heat into work, so that you've sort of recovered 30% of the energy which was just going to be wasted. So for example, this cycle gave 60% efficiency, and the Q out, for example, was about, let's say, 100. Okay, so 100 kilojoule. Now if you can utilize that 100 kilojoule and per second, let's say, and utilize that 30% of that 100 kilojoule, then that means that you are only wasting 70 kilojoules instead of the 100 you would have to waste. So the advantage of this cycle is, for example, even if your primary cycle was like at 35% or 40%, and if you add the secondary power plant, like for example, you use the exhaust gas to heat up steam and then use that steam to produce power as well. So now your overall plant efficiency can easily exceed 50% of the total energy provided by the fuel. So that's a very good mechanism. And similarly, you don't need to, for example, waste all of the steam as well. So that steam can be used for different processes as well. So that steam can be input as for cogeneration. But this has a disadvantage of adding complexity to the system. So instead of just having a simple gas turbine or a simple steam power plant, now you have both utilizing the same energy source and but producing uh, not like it is involving a lot more cost, but the return of investment might not be uh, that good of each plant operating separately. So for example, the gas turbine can give you a return X, and the steam power plant gives you a return of investment Y. So the return of investment ROI of X plus Y will always be less than ROI X plus ROI Y. Okay, this is the basic concept that you can increase the efficiency of both of the cycles, but overall you have to add a lot of cost initial systems. So this example is again, you can uh, you the gas enters the turbine at 1300 Kelvin. Let's just ignore the isentropic efficiency of this turbine and compressor for now. Um, let's just say this gas exits at so the pressure ratio of 8. So that means that we take the PR at 1300 Kelvin and we divide that by 8, and we take the PR at that value and we find out the temperature T4. Okay, so we also have the high temperature of this steam, which is 500 degrees Celsius at 7 megapascals, and we have the so we have all of the data given, which is um, the ratio of mass flow rate of the steam and the combustion gases, and the thermal efficiency of the combined cycle. So this is the first part is simple enough. The mass flow ratio will be, for example, m of air multiplied by delta H of air will be equal to m of water multiplied by delta H of water. So you can utilize that and find out this ratio. And the thermal efficiency of the combined cycle. The combined cycle has this part, which is Qn, and um, this part plus this part, which is Q out. So you can just add both of these, and um, so you can have H450 minus H300. That will be the Q out here, and you can have the H4 minus H1, which will be the Q out here. What I will recommend you to do is you need to take the mass ratio of this air and water as well. You don't need the exact mass. We are not given the actual, yeah. So since we are not given the actual mass flow rates of water and air, you can just take the ratio that, for example, whatever m air over m water you get, you just use that to find out what is the Q out and here Q out as well. So add both of these, 1 minus Q out by Q in, and you had the Q out from both the air and the steam. Okay, this was um, so another type of combined cycle is a mercury water vapor cycle. So mercury has the advantage that it boils at, for example, a much higher temperature than water, although it maintains a similar viscosity and sort of characteristics as a water power plant. So since it is a liquid at normal temperatures as well, so it can have a steam or a gas vapor power cycle at a much higher temperatures, as we can see here. And since we can get uh, the steam the mercury condensation to be at a very high temperature, we can use that sort of heat to boil water till point 4, for example, and then add just a superheater to get this water to point 7, and then use this as a second cycle. It has disadvantages, as we can see, that again, A, we can have a very high efficiency, and B, we can use mercury at a very high critical temperature compared to water. So you can but why don't we see any mercury power plants? First off, this is not a very economically attractive solution because mercury is very expensive and mercury is very toxic. So in order to actually construct a plant like this is a very expensive project, which again does not give you a return in which is justified by the which can justify the initial cost which is added to the system. So again, you will not see a lot of the mercury water combined cycles, but you can see some of the gas steam combined cycles as well, especially if you are dealing with a very large power plant, or if you want the steam to be utilized in some other processes as well. For example, if you are in a food processing industry or some chemical processing industry, you need to produce steam as well. So what you do is you burn gas in your gas turbine, you produce power from it, you use that exhaust gas to boil steam, you take some power out of it as well, and then you use the remaining steam at a low pressure to run your processes, whatever you want, for example, in any chemical process or anything. So this concludes our lecture on the Brayton cycles and the gas turbines and combined cycles. We will have the discussion on Tuesday, inshallah. Regarding that, I will recommend that you solve the later examples we saw by yourselves, and also the example 9-5 to 9-7, and try and solve examples with, for example, two intercooler and reheaters or three intercoolers and reheaters, and just see the effect of regeneration. Assume the regenerator effectiveness as 100% or 80%. Just see the effects of all of these. So we will have a meeting soon, and this is goodbye from